Hello developers, let's start developing. My name is Veko and tonight we're gonna take on the second part of task 22 of 2021 Advent of Code. Lots of tools in that. So we solved the first part easily with brute force. So if we have these boxes, these cubes or cuboids technically, that are turning on and on and off and on, we are making a huge cube 101 by 101 by 101, and that's a lot of points. How many points? 101 times 101 times 101. Yeah, about 1,000,000 points. And then we're going through all of the data and for each, a triple for each, and if something is on, turn it on, otherwise turn it off. When we're done, we're just calculating how many ones we have. We are summing across all that huge 1,000,000 point space and we're done. And that was all we needed to do for part 1. Very fast and easy solution. Unfortunately, for the second part, we have input like this. So the second part is totally the same as the first one. You have these operations, commands that you need to do. So this means all the items between -5 and 47 on the X scale, between -31 and 22 on the Y scale, being between -19 and 33 on the Y scale. Well, let's put them on. And yeah, a for loop and triple nested for loop can easily do that. But then you have things like this. So let's see how that will fly. So let's count how many points we'll need to run through if we run this through a for loop. That's X, that's Y, that's Z. So first of all we will need to, you know what, I have a program for doing things like that and it's called Excel. So this is 2 minus from, actually +1, because we are doing inclusive thingy. So that means that 57795 should be turned on or off or whatever. What was it? I guess it was on. So this should be that one minus that one. This should be that one minus that one, +1. Yeah, I forgot +1 here. And this one is again that one minus that one, +1. So we have, and now we have this number and this number and this number. And in order to get how many points there are, we just need to do a simple multiplication. That times that times that. And that's Excel actually kind of refuses to show the whole number because it's kind of too big. It's 1 with 1.5 and a lot of zeros behind it, so it will be something like 1539, that's 4, and then we have 14 zeros, 9, 0, and now 10 more, 1 2 3 4 5 6 7 8 9 10. Yeah, that's that many thousand, that many millions, that many billions, that many trillions, 153 trillions. Yeah, doesn't matter. So a for loop might have some issues running across 153 trillion points for, and don't forget, that's one of these. And we have about 100-ish of those. Well, actually, once you hit this scale, 100 is not that big a number. We just add 2 zeros. We have a lot of them already. So what will this become? just 15 quadrillion. Does it sound, to be honest, to my ears, 150 trillions or 15 quadrillions doesn't sound too different. There are a huge, huge number that is beyond our reach. So, yeah, straight brute force won't work about this on this. But how about a modified brute force? And just a second, let me explain the situation we are. The event is actually done. We opened the 25th task. We have all the tasks, all the puzzles are open for us. We just need to finish them. And I still have these two to finish. So I have actually did some code that solves this offline, so I will kinda reiterate over the steps I've already taken, and I will write some code, but I will copy and paste some code. And I have at least two solutions here. So, first of all, how do we approach these thingies? Because you saw, calculating the volume on this is trivial. And this is the volume. It has about this much dots or cubes. They are actually cubes, the pixels that we want to use. They are some kind of weird cubes. So just a sec. There are some weird cubes, so that we are turning on and off. We have that many, and that part is easy. And if we can somehow manage to determine all the places where these things are intersecting, we could calculate how this thing goes. So that is one approach, and that is a very straightforward approach, and basically I think that's the intended way you're supposed to solve that. And since we have a lot of these cuboids, something called the inclusion-exclusion principle comes into play. And to be honest, that's one of my least favorite things to implement in code. And what is it? Let's see. Let's have a few prime numbers. 2, 3, 5, 5. And let's add 7 for the fun of it. So, and let's start with a huge number, let's say 10,000. How many numbers under 10,000, including 10,000, are divisible by 2? Well, we can count them. That's one way to do it. We can say, okay, 2 is divisible, 4 is divisible, 6 is divisible, and so on and so forth. But that kind is boring. What we can do, we can just say, divide this by this. Actually, I'm gonna use there isn't a div method now? Okay, I will just divide this with E1 and I will fix the div. So we have 5,000 numbers and are under and including 10,000 are divisible by 2. How about 3? Yeah, we need to take the floor function as well because we need to dial it down. A number cannot be half divisible by 3. So how about for 5 it's 2000, how about for 7 is 1428. Yeah, we got those numbers. And that part is easy. But what if the question is how many numbers between 10,000 and are below 10,000 are divisible with 2 or with 3. So we count them if they are divisible with 2 or with 3. So we count 2, we count 3, we count 6, we count 4, we don't count 5, we don't count 7, we count 8, we count 9, we count 10, we count 12, we count 14, we count 15, and so on and so forth. So how many of those numbers? Well, instinctively it's gonna be, well, that is easy. We take how many are divisible by 2 and how many are divisible by 3, And we get an incorrect answer. Why? Because in these 5,000 numbers are 2, 4, 6, and so on. And these 3,000 and something number are 3, 6, 9. So we're counted 6 twice. So now we need to take away 6, we need to take away 12, we need to take away 18, and so on and so forth. So we're gonna have to divide this by floor mat of this thing divided by 6. And this is the actual number of numbers that are under 10,000 and divisible with either 2 or 3. So we can do this for any pair. So this is 2 and 3, if we do it for 3 and 5. And since these are relatively prime, these are prime numbers, we can just say, well, it's divided by this thing, divided by this thing. And we'll get the value. So for 3 and 5, yeah, of course, we're gonna fix D1. And then we'll manage somehow the others. So this is 3, this is 5, this is this one, this is this one. Yeah, we have that many are divisible with 3 or 5. How about 2 and 5? And we need to, this is 2, this is 5, this is this is, oh, and this is this. 6,000 are divisible by 2 or 5. Well, great. And of course we can do all the combinations, 2 and 7, 3 and 7, and so on and so forth. So, it was okay. We're counting 2s, we're counting 3s, we're subtracting 6s. But what happens if we want to see the numbers that are divisible by 2 and 3 and 5? Well, how do we do that? Well, we need to add these numbers and these numbers and these numbers. Okay, so we got more numbers than there are numbers. We have 10,000 numbers and 10,300 of them are divisible. Of course not. So we're gonna subtract all the 6s, so to say. And we're gonna subtract all the 15s, so to say. And we're gonna subtract all the 10s. And we got 7,001, but this is the wrong answer. Where does this answer go wrong? Well, yeah, here we use the 6s. No, not minus 6. Remove the 6s. Remove the 15s. And remove the 10s. Because the numbers that we are removing here, because we added them twice, are 6, 12, 18, here it's 15, 30, 45, and here is 10, 20, 30, and so on. So here we removed the 6s, and we removed the 15s, and we removed the 10s. And that is all fine and dandy. But let's see what happened with the number 30. So 30 got added once because it's divisible by 2. It got added once because it is divisible by 3. It got added once because it's divisible by 5. And it got removed once because it's a 6. It got removed once because it's a 15, and it got removed once because it is a 10. So this number just doesn't include the 30s. So 30, 60, 90, and so on and so forth. Those are completely removed. We removed too much. So now we need to go back and actually add the next batch. So this is gonna be divided now with EGF. Yeah. So, and we don't need to add those, we remove those, we need to add those. And this is the number of numbers under 10,000 which are divisible by both 2 or 3 or 5. And if we continue this example including 7, we're gonna get bogged down because let's just look there. The problem will be with 2010, and we will 2010, it's a 2, so we'll add it. It's a 3, so we'll add it. It's a 5, so we'll add it. It's a 7, so we'll add it. It's a 2 and a 3. I'm just gonna write it this way, so we'll remove it. It's a 3 and a 5, so we'll remove it. It's a 2 and a 5, so we'll remove it. It's a 2 and a 7, so we'll remove it. It's a 3 and a 7, so we'll remove it. It's a 5 and a 7, so we'll remove it. So far we've gotten that we've added it 4 times and then removed it 6 times. So far 210 appears minus 2 times in our list. Okay, we need to put it back in. It's a 2 and a 3 and a 5, so we're gonna add it back in. And it's a 2 and a 3 and a 7, so we add it back in. And it's a 3 and a 5 and a 7, so we're add it back in. And are we done? What is the actual sum of these? Yay! So we got, and actually it's supposed to be superior just one, because under 10,000 there's just one 210. And we are somewhere around correct, but not really, because it's also a 2 and a 5 and a 7. So we need to add it once more. Let's have the sum actually somewhere around here, and that will be the sum of everything up to and including the 2010. So now we have two 2010s. Okay, no problem, because it's a 2 and a 3 and a 5 and a 7. We'll remove it once again. So that means that we have just a single 210, and most likely it's correct. And now so we can do something very similar, and I think that we were expected to do something very similar with our cubes. So you have some kind of a volume of the cube, and then you have another cube that kind of intersects it, and then the sum of all the lit small cubes will be this volume plus this volume minus the volume that's in both of them, because we counted it twice. And then if we have a third cuboid on that volume, it's the volume of the first one and the second one and the third one minus the one that's in the first and the second one, minus the part that's in the second and the third one, minus the part that's in the first and the third one, plus the part that's in the first one and the second one and the third one. And then if you have a fourth cube, and so on and so forth. And this is actually codable. There is a algorithm how to implement the exclusion-inclusion principle. And actually this is why it's called exclusion-inclusion, because sometimes we're excluding things, sometimes we're re-including them, and so on and so forth. Yeah, so we include, you can get the idea that we are including on odd passes or excluding on even passes. So the second and the fourth pass are exclusions, the third one is an inclusion, and so on and so forth. And there is some quite funky math here. There should be an algorithm somewhere around here that will tell you how to implement this and so on and so forth. And I've actually implemented it once or twice, but each time where I am implementing this, it's incredibly error prone, it's incredibly hard to debug, impossible even, because you have no idea what the correct value should be or where it should move and how it should be, because you might have a value. You saw that the values that we've gotten here as we were counting them were sometimes very low, sometimes were very high, over 10,000 maybe. So I don't have a feeling that we're progressing as we're working. So I cannot say whether the algorithm is operational or not, because we can only look at the end result, and it is still just says 7,500. Take it or leave it. So it might be wrong, it might be correct, and it's if it is as an advent of code task, basically it would be it would run for some time, we would get the value, copy and paste it, and then pray to Jesus, Shiva, Buddha, what have you, that it is the correct one. We cannot be sure, and I quite don't like those kind of programs where I hope that the value is correct, because I really have no idea whether the algorithm is correct. So, just as I saw this task, I said, no, I don't want to do the exclusion, especially as it's not a straight exclusion. So we have some steps that are turning things off. So we will need to somehow exclude those on an include branch, or include those on an exclude branch, or something like that. I have no idea, and it would have been even worse. And the only thing that we can go for is basically this. Well, actually, I will more likely be focusing on this input, as this is actually a full task, and we're gonna abuse the heck out of the fact that, yay, it pasted nicely, that the first part and the second part are exactly the same task. So whatever algorithm we're gonna do, it should work just as fine and just as correct as the first task. For the first task, we had basically this input because we cut off everything else. So if it works for this and it works for this, then maybe we can try it on this. If it works for this, then try it on the full scale and see what sticks. So first of all, I'm gonna remove these. Yeah, I could have done it with the formula, but sometimes you just need to edit. And let's add headers: action x from x2, y from y2, z from z2. So the first thing that I want to do here is normalize it. And normalization, I think I already did that actually. Yep. Is make sure that everything goes down to, because we're going to have a lot of positive and negative numbers. This example only has positives, but we have a lot of negative numbers here, and it's relatively symmetrical. What I will do is actually move everything from wherever it is to the origin. That means that I can get the minimum out of all these numbers for x and for y and for z, Unfortunately, all of this is symmetrical, so it's the same. And then I can calculate this value minus the minimum. And it's a given that that number will always be at least 0. So these four numbers have to be positive. Let's hard code that as well. So this is for the y's, for the x froms, x2's, so to say. This is CD6. So copy paste, paste, paste. Oh, copy paste, 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 paste. Just move it over to the other 9. Yeah, it's a 9 is a 9, but still. So now we have our nice coordinates. And we have our on and off and on. So in this case, what I can do, I can kind of brute force this. Because I have a range on x, from 1 to 4. So let's analyze. One thing that is important is that the x and y and z coordinates are kind of independent. There is no relationship with them. If x is something, it doesn't mean anything about what y can be. And if x and y are something, they don't give you any data about what z could be. It could be basically anything. So what I want to do is to somehow separate this on different coordinates and then somehow do some kind of integration when we're merging back and counting. So I will create an array of all the possible integers value. That's 0, that's 1, that's 2, that's 3, that's 4, and that's it. So now I will say for the first one from 1 to 3 we have this thing 1 3 1 3, and let's just do it as a string. For example, yeah, this is tedious in Excel, this and this value and a comma and this value and a parenthesis, comma, parenthesis, and this value and a comma and this value and a parenthesis. Yeah, this gives me a nice interpretation of this. So these are the y and z coordinates of this segment, and those exist only if x is 1. Copy paste values so that I can work with the values and not with the formula. So this exists for x1 and x2 and x3, and this thing exists only for x2, copied the wrong one, for x2 and x3 and x4, and this one exists only for x0 or x1 or x2, and this one exists only for x1. So we have some kind of a map right now. We know that for 0, for example, we only have this. Let's kind of flip this map on its head. 1 2 3 4. So at x0 we only have a single segment, so this cannot intersect with anything because this is basically a square right now. or a rectangle or whatever. Yeah, so this is basically a square that does not intersect with anything, and we can calculate exactly how many lights are inside of it. And of course, we need to take care which of these is on, which of these is off. So we're gonna color this, yeah, like this. This is off. So for the 0 index, we know that we will only have on and nothing else will touch this. If it would have been touching this square, this rectangle, it would have been in this column. It's not, so we're not touching anything. So we know that for x0 the value will have to be 3 by 3, 0, 1, 2. So the formula it will actually be 2 minus 0 plus 1 times 2 minus 0 plus 1. That's x with the y dimension, the z dimension, times 1, because we're only counting it for 0. This is a minus. Yeah, so we're getting that 9 lights will be lit for x0. And now we have the situation for 1, when we have this area, and this area, and this area. And we have this situation for 2, where we have this area, and this area, and this area. Situation for 3, when we have that and that. And again, the situation at 4, when we have just 1. So again, 4 minus 2 plus 1, it's again gonna be 9. So we somehow broke down our problem into 5 smaller problems. Out of those 5 smaller problems, 2 got solved trivially, and we right now are left with 3 more problems to solve. So let's rewrite the problem, but note that x and y, x from and x2 are just not important right now, because for these, let's solve it for 1. So we have an action that will be on, we have 1 and 3 and 1 and 3, and we have an action that will be off, and we have 2 and actually 0 and 2, and weird way to say 2. And we have an action that will be on that says 1, 1, 1, 1. And now we can do the exact same thing that we did with the x's with the y's. So we have, but now, since we're only doing it for a limited set of y's, we don't have to have such a huge range, so to say, because you can see that y actually goes from 0 to 4, same as the x, but we are not solving that case. In the data we have, we are going from 0 to 3. And I'm gonna use this to copy things, but now we don't need the y part, we just need the z part. Yeah. So from 1 to 3 we have this thing. Paste as values. From 1 to 3 we have this thing, and from 0 to 2 we have this thing, which should be red. And from 1 to 1 we have this thing. So let's normalize it this way. So this is for x0, x1, y0. We are solving this case, 0, 2. This is all the data we have. So how many will be lit? Well, none of them, because we're just turning some off and they were already off. Thank you, goodbye. We have a 0. For x1, y1, we have from 1 to 3, and then we're turning them from 0 to 2, and then we're lighting them from 1 to 1. And now it's gonna be trivial to execute this algorithm once more for z, actually, but we are just dealing with the units there. And it can be trivial to see that we're gonna turn on 3, then we're gonna turn off 1 and 2, and then gonna turn on 1 again. So we're gonna be left with 2 lighted thingies. Similarly for 2, we are turning on 3, turning off 2. For x1, yz2, we will have exactly 1 lighted thing, 3. Because 1, 2, 3 are on, then 0 comes off, it's already off, 1 comes off, 2 comes off, and we're left with, unfortunately, the 3. And this is a straight up thing, because we are lighting from 1 to 3, and we will have 3 lit lights, or for x1 we will have 6 lit lights. And let's copy this here. We have 6 lit lights for 1, and we can do the same thing here. And let's not get tedious. So since this is already a 2-dimensional matrix, we can say, okay, 0, 1, 2, 3, 4, 1, 2, 3, 4. We're gonna brute force this. Light from 1 to 3. Yeah, this is actually what our brute force algorithm does. Light from 2 to 4. Turn off 0 to 2. That's no fill. How many are left? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, we have 10 here. And for the other one, oh, we have 10 here. And for the other one, we're just not doing the thing that we did from 0 to 2, so it stays like this. So we have 1, 2, 3, 1, 2, 3, 4, that's 7, and 7 again, that's 14. And that's how many lights are on for each of the x's. And then we can just sum everything and get an incorrect answer, because the correct answer was 39. What are we looking here wrongly? Okay, you get the picture that, yeah, I'm summing somewhere incorrectly, but in essence it will be exactly the same thing. Maybe this 6 is incorrect. No, it cannot be. So this is, we do have a 0 and we do have a 1. Is this a 9? Yes. Is this a 9? Yes. Let's see. Most likely these two are somehow wrong, but doesn't matter. So, as you saw, this is much more complicated than brute forcing it, but it is in brute forcing in the sense that we are not thinking about what is and what isn't, but we're just going through the motion. It's more or less automatic. So we're taking our x values, sorting them out, and just filling them with the y and z segments. And then for each x value, we're taking that and then just plugging it in and doing it on the z segments. And I actually did that. Yeah, this is the algorithm I had. So we're taking the maximum value. We're just for initially we're just moving everything across the x axis because we don't really care what numbers are on y or on z. And then you can see that we are creating an array that is that wide, that has all the x values. We will, for each, so for 0, for 1, and for 2, and for so on, we will see which of the commands are basically intersecting our index. So we didn't go in the explanation. I went that I distributed the commands across the scale. We can go the other way and say which one of these intersects with 0. Okay, which one intersects with 1, with 2, and so on and so forth. Which one intersects with 1 and 2 and so on and so forth up till 200,000. That's the most we're gonna get in the live example. And just put that action sans the x coordinate, because in this case we know the x coordinate. It will always be index. And we have then we are splitting them into two cases. So we have our simpletons, which basically have only a single action inside of them, as we had for 0 and for 4. And yeah, this is the 9 that we are missing because this is a red one. We forgot to color this one red, so this 9 is not there. Okay, solve the bugging in Excel. So what do we have? We have the simpletons that have just a single command, and if they have a single command, then if that command is on, we're counting it as a singleton. If that command is off, we don't care. If a cube only gets one thing done to it and that thing is to turn it off, well, it was already off. Yeah, that's a 0 anyway. Otherwise, we pronounce it that's a complicated, and we are pushing it to the complicated array. And that will have multiple segments, so to say. We can just calculate the singletons, and the formula that you saw used is the exact same one. 2 minus from plus 1 times 2 minus from plus 1, and that's the total number of single segments. And then I'm actually doing a bit of a trick that was not visible here. But for example, if this was 10 instead of 4, just that one. So that means that the number 4 had 2424. The number 5 would also have 2424. The number 6 will also have 24, up to the number 10, which will have 2424. So if we have multiple x's with exactly the same set of segments, so to say, let's call the y the z thing segment. If we have the run like that, then we can just merge it into a single hyper segment, or whatever you want to call it, that will actually be a straight up limited in x scope. So during that x scope, from 4 to 6, from 4 to 10, nothing will change. The x and z values will be completely static, and we will be able to reason about them. So if we solve that for 4, we can just multiply it 7 times to get the 4 to 10 division. So I'm merging the segments because as I run it on the huge example, we will get out of 200,000, we will get something around 2,000 simpletons, and 990 other thousand will be compacted to something like 300 or 200, 300 intervals, so to say. And if we have those 200 intervals, then this is the merging code that says start from 1 and see is the next one identical to yours. If the next one is identical to yours, pick it up. If it's not, then we're done. Push the one that we're working on so far and continue. So we reduced that many complicated segments to that many merged segments. And then for each of these segments, we are more or less running the exact same thing. So the exact same program. I didn't bother too much with substructures here. So this is the exact same program, only every x is transferred to y, and we have an additional xdiff value, which is actually how wide our x hypersegment is. And we're doing the exact same thing. We are counting the intersects, we are creating a huge array of epsilons, we are counting the singletons, we are counting the complicated, we are counting the total singletons, merging it completely, reducing, and after we're done, we have basically all the data that we need on the x and on the y. So what we're left is with what it's called here a y interval segment. So that has that width on the y scale, that much width on the x scale, and that many segments on the z axis, which have an xdiff, an action, and the z interval, so to say. And of course, after we're done with the x's and the y's, we are starting with the z's, and the z's actually do the exact same thing. Once more, we're translating to positive, but you know that we have one dimension only right now. Processing, simple, not complicated, merging the complicated, and after we're done, we can just take care of everything. And you know what the issue is? If we have multiple merged segments right now, each merged segment on the XYZ scale has a field, a three-dimensional cuboid with exactly the same sequence of things that will happen. So it has a set of actions that will happen on that. So we will have a situation, for example, if we had and 6 and up to 10, so to let's just use this one. So we have something that is 1x, white 1 on x scale, 3 on the y scale, and 3 on the z scale, that will have the exact same set of commands effective on it. And each of those commands will be effective on that cuboid, and none of them matter except the last one. Because if you have, then our task basically devolves into, you have a set of commands that will turn on or off the whole field. if you limit this field to 42424. So if you turn it on and then you turn it on again and then you turn it off again and off again and off again and on again, it's gonna be on because that's the last one that got done. So we're just saying if the last action is an off action, no lamps are lit. If the last action was not an off action, then all the lamps are lit. And that's ydiff times xdiff, xdiff, ydiff, z to and from plus 1. And that's all there is. And let's run this 22 full brute. I just need to say that load this from this file. And let's run it on the trivial smallish input. Yeah, I have a lot of logging code inside of it, and this time we reduced 3x segment to only 3 merged x segments, and those 3 segments are basically 1 and 2 and 3 because 0 and 4 already got pre-calculated. 7 y segments were merged to 6, 13 z segments were merged to 9, 8 on lines that were handled by more than one command, and the total result is 39. And that is correct. And you can see it was only 5 milliseconds. So this works better for our original input than the straight up brute force. And let's take our original input that we had. This was the actual task that we needed done. (533, 863, 533, 863). This is 212 milliseconds. This is 9 milliseconds. Weird. Yeah, but I guess all the console logs are maybe bothering it because I was testing, this is relatively faster. Never mind, we managed to solve our task, and let's take a third example, the one that was given here, actually this input. (597.84, 597.84). This works perfectly and it's perfectly correct. But there is a small issue. And that issue is not actually that this is too slow. It is. It's not fast by a long shot. But there is another problem with it. Yeah, this is Node. And it's running, and it's running, and it's running, and it's running, and it's eating up memory. Yeah, you can see it reduced 195 X segments to only 825 merge segments. And it's running, and it's running, and it's running, and it's eating memory, 4 gigabytes of memory. And it ran out of it. By default, if you don't specify it differently, Node is somehow limited to around 4 gigabytes of memory. And we filled everything, and you might have not seen this screen, but I've seen it my fair share of times, both in experimental and in real world scenarios. This means that Node ran out of memory. One way to do it is to add more memory. But I did some tests and some calculation, and it seems that this algorithm, it's quite possible that I would be able to optimize it and make it use less memory, but as it is written, it will take something around 200 gigabytes. So if you have a machine with more than 200 gigabytes, you are free to run this program and it will give you your solutions perfectly. And that's quite okay. So at this point, I was just thinking, well, that didn't work. What else can I try? And I was almost at the point when I would have used inclusion and exclusion, but I said, no, I'm too stubborn. I'm not gonna code it like that. I'm gonna do some other trick. And I actually thought of a trick that I thought that will be maybe not the fastest thing in the book, but it will be brute forcey enough, so to say. You might have noticed that I love brute force. And the reason I love brute force because usually brute force is a generic example. Is a generic strategy. So every problem is solvable with enough brute force, theoretically. It doesn't matter whether you're opening a jar, whether you're opening a door, or you're opening a bank vault, or yeah, you can knock on it until it's open. It might not be the smart thing to do, but it works. It might take you more time, but it works. You don't need to have a specialized solution to each situation. Sometimes, and I want to usually have a brute force solution, brute force approach to a lot of problems, because for a lot of problems, as hardware goes better and better, brute force is an okay approach because it will be relatively low code complexity. Anybody can understand that code, and it runs just as fast as a fancy optimized algorithm that nobody understands. Note that for code that executes once a day or 3 times an hour, a runtime of 20 nanoseconds and 5 milliseconds is exactly the same. There's no difference. One of those is much faster than the other one, but again, for the end user, there is just no difference. So I would always go with the clear code that is understandable, that is maintainable, that I know what it does, that other people know what it does, that they can change it and modify it and adapt it to something. Then a fancy home-baked hashing algorithm or something like that, that will work extremely fast, extremely well. But if I get hit by a bus, they will just have to throw away and replace it with something else. So I don't like that approach. So whenever I can, whenever it's feasible, I like using brute force because it makes sense. I like using analytical solutions, and they're great, but they have a greater, so to say, learning curve. And they might be too specialistic. So you might have a ready-made and ultra-fast analytical solution that works for your case, but then that case can change very slightly, and your algorithm just doesn't work for that scenario because it has some built-in assumptions, so to say. Brute force makes no assumption. Hassan, chop. You just go in and do whatever you want. So I'll have a smoke break and then I'll return with what I ended up doing. Just a side note, I am quite confident that the algorithm I did is correct, and I'm quite confident that it works, but to be honest, I haven't checked it live. As you can see, this still doesn't provide me with a star, so we might have some debugging if this doesn't work. I'm quite confident that it will, but let's see. So let's get back to the task. and see what I did another thing as an analysis. So I decided that while this straight brute force, when we are just unpacking everything, where are you, yeah, this few lines of code, when we are unpacking all the data on the x-axis, for example, and we're just looping through each of them and then merging. This part is way too intensive and takes too slow. But on the other hand, what if I could just start and build the merged map? Because the merged map seemed like a good idea. What if I'm able to start and do that from scratch, so to say? But in order to do that, I would need to have some kind of idea how things intersect. So more or less this might be not really a inclusion-exclusion thing, but something along those lines, but with coordinate separation. So we're gonna separate everything out on the coordinates, and still we're gonna use all these segments on the X and on the Y and on the Z scale, and seemed like a nice idea. So I started with that, but I ran into a problem. That when we're intersecting something, we have no idea how that thing can intersect with other things, and I didn't know how to actually do it efficiently, because there are lots of ways for two things to intersect. And I started thinking, basically, what happens if I have one segment that is, let's say, it's from 5 to 7. How many different ways can we have an intersecting segment? And usually this number is less, but now we have something that is different from usual case, because we have thick cubes, because our intervals are inclusive. So interval from 5 to 7 means that 5 is included and 7 is included and everything in between is included. So this thing can get intersected in actually 9 different ways. And those 9 different ways are 3 squared, because our interval we have our second interval, so this is a given, this is a fixed interval, and we have some other interval that intersects it. Of course, one of the options is that they won't intersect at all. Basically, the second one, they don't intersect when the second one finishes before the given started, or when the given finishes before our thing started. Okay, those are trivial to fix, but how can they intersect? And the nice thing here is that we have no middle ground. If we have an 1, 2, or 2, 3, 4 interval, these intervals don't intersect, because 5 is not included in the first one, only 4 is, and 4 is not included in the second one. So we can have an interval like this, that starts before the given and ends before the given. Starts before the given, ends with the given, starts before it, ends after it. Starts with it, ends before it. Yeah, this will be identical with this, so to say. Starts with it, ends with it. Starts with it, ends after. Begins after, ends before, begins after, ends with, begins after, ends after. So those are 3 options for where it starts, 3 options from where it ends, and we get a total of 9 combinations. And that's great for a single dimension. So we have 9 combinations for a single dimension. and I went in, and this was the tedious part. I actually said, how will this affect the groupings? So we have three groups in this case, in the first case. We have the group 4, which is the part of the second interval that is before the first one interval. Then we have the 5, which is the part where both of them get applied, and then you have a third part which is 6 and 7, which has only the second one applied. Again, the first one applied, both applied. Second one applied, both applied. Second one applied, both applied, second applied. Both applied, first applied. Both applied, both applied. Second applied, first applied, both applied, first applied. Yeah. And all of these are from the viewpoint of the first one, so to say. Because you can say, well, isn't this case and this case the same? Yeah, but because you have one interval that is wholly inside another interval. Yeah, it is the same situation, but not from the viewpoint of this interval. And I'm always going to take the viewpoint of this interval. So I will have some kind of a set of all the intervals, all the existing intervals so far, and I will take a new interval and try to merge it on top of that. And I can use these rules. And I have that here, and now I will just start copying and pasting things. So, of course, for the first thing, what we're gonna do, we're gonna translate everything to the positive side. Let's get back to this. And that's cool. Because now we have everything to start from 0 and everything is positive because negative numbers make my brain hurt. So that one is okay. And one very important thing that I want to do is I actually want to sort these. Why do I want to sort them? Because then basically sort them from the start point. So each time I'm adding a new segment, all the segments that begin before it are already added. So I can always count that there won't be another segment after me that starts before this, that will get mixed up somewhere before this. In that case, I can just say, I can get all the intersections. So basically, if I have many intersections in my set, and they will be all be distinct, so I will have a segment like this, and 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 I will take care that I am distinct, that they are all distinct. There is no overlap. Basically, that's what we're doing. We're removing the overlaps. And we get with a new segment that is from here to here. Yeah, let's use green. So that means that we can only have a few specific cases. We can actually encounter all 9 cases somewhere, but you can see that for most of the cases we need to take this part and add it to our list of segments. We take this part, add it to our list of segments. And what will happen for this specific case, we're gonna split this interval into part 1 and part 2. So this only will get another color. Let's use something bluish. And this interval will get split into 2 intervals. Yes, use something other bluish. So after we merge this interval, we are left with this situation. So it will be quite easy to merge intervals on top of one another. And of course, if we get lucky and we have an interval that's just like this, then we're just add this part, add this part, add this part, add this part, and that's it. Anyway, I needed to handle all of those cases. And all of those cases are kinda iffy to deal with. So, I created an extremely convoluted, actually not convoluted, it's not convoluted at all, but it's an extremely long method. So, I'm getting a list of all the intervals, because that is my result, so to say. And I'm getting a list of intervals that are intersecting with my segment. This is my segment, and this is the command the interval I'm trying to merge inside of them. So we have intersects, and they are distinct and sorted by coordinate, and it's not possible to intersect two of them simultaneously just because they are distinct. So we're gonna find the index of our the intersect that we're trying to reason about. And then, case 1, if we begin before the intersect and we end before the intersect, we split to 3, 4, 5, and 6, and 6 and 7. That means that we have these 3 intervals, and the first interval stands from command from the 4, and ends 1 from the beginning of the intersect. And it has the segments from the new guy. That's the segment for the new guy. It only has that segment. We have a middle segment where we take both the new guy and anything that's already existing, and then we have a third case, which is the 6 and 7 here, when we have everything that the intersect already had. And I'm using this in order to copy over the same segments. So if we have multiple technically I don't have to, because I can say, well, this kind of remains the same, but let's be on the safe side, because I've had some situations when I'm changing some segments and then I'm changing somebody else's segments because we managed to have the same reference to the same object. And I will remove the original interval in the original intersect from the list of all intervals, and I will push in these 3 intervals. So what we're gonna do, we're gonna remove 4, 5, 7, 5, 6, 7, and we're gonna have 4 and a 5 and a 6, 7. And all of them will be distinct, all of them will be sorted. The same goes if we begin before the intersect, but with the intersect, then we have the third option. And if we begin with the intersect and we end after the intersect, and here is the optimization, so to say. Because if we go back to this case, yeah, let's have it that color. Here we have one interval, a second interval, and the third interval I'm not touching, because I know as for a fact, because they are sorted, that we cannot have a situation when my top is intersecting with more than one interval. My top will intersect with exactly one interval, and that interval will always already be there, because if it wasn't, it wouldn't have been sorted in front of me. So these situations, can only occur on one of the intervals. Yep. So what I will do is I will basically, let's copy it over. So this will be one interval, this will be another interval that we decided that it's gonna be bluish, and I will just remove the top of the current interval and continue on. And now we have the case when it's basically this thing. And again, I will take care of this part, but not this part. So we're just gonna say, okay, this goes here, and we're deleting the top. And then this goes here, and we're deleting the top. And then, this was full color. It's not different. Let's have some other weird color. Let's use that. And then we have this intersect, so we will split this. So this will become another of the blue ones, and this will remain. So, and okay, we can, and we have another case actually where we are going past the last interval that we have, but if we have that case, at the end, whatever we left, we can just do this. So, starting from this scenario, we got to this scenario in a deterministic way, so to say. And we basically right now have again, we started with a sorted and distinct list of intervals, and we ended up with a sorted and distinct list of intervals. So that's why when we have an after part, we split to two. One before the intersect, one together with the intersect, and the part after the intersect is considered on the next run of the for loop. And that's this for loop that runs through all the intersects. So we are doing this here. Oh, no. So basically if we are done, this signifies that we are done because we are basically throwing away our original data. We're done with the intervals. But not in this case. If we have an after part. So note that if we end before the end on the intersect, this means that we are on our last intersect. Because we cannot have another intersect that comes after the one where we end. Because we do not intersect. So we know that if we are doing that, then we're done from, we are setting our command to be into an invalid state because from is after 2, and we don't need to run anymore. Same here, but not here, because this means that we do have an after part, and I'm just skimming off the top enough so that I begin after the previous intersect ended. Again, we're done if we're the same. If we have a part we end before the intersect, we're done. If we end after the intersect, we're not done. Skim from the top, we are done, we are done. So out of the 9 cases, in 6 of them are only the terminal cases, and we only have 3 cases when we need to continue running. The cases when we have an after part. And if we have after part, what we're doing is skim from the top and continue. And of course, once everything is done, we just splice the last part, that's this, the tail. And to be honest, I had a bug here when it didn't get spliced in the correct position, and I tried to mangle the indexes somewhere, and at the end gave up and say, okay, resort everything. This is not strictly necessary. There might be a way to get rid of this command because they should be sorted by definition, but sometimes they're not, and I got tired of chasing the bug. And I have some weird types here. So we have something that's called a segmented interval of t. Why do I need a generic? So, because the command is a really simple interface. It's just an interval. It has a from and a to. But the segmented interval will also include the segments. So we'll have a from and a to and segments that are connected to that interval. Because don't forget, each of these intervals, actually it's not the interval itself that we are interested in. We are interested in the unique set of segments that are spread out through it. When we are separating x, we are interested in the y's and the z's that are connected to it. We are not calculating them, but we are interested in them. And since sometimes the segments will be the segments on the x and on the y and z axis, sometimes they will be segments on the z axis itself. That's why I needed this part to be generic. So yeah, we have execute intersect. So this will execute something when we are giving it a whole list of segmented intervals and a given set of intersects. Actually, we can do the intersects here. Yeah, we might refactor that part a bit. But let's see how we use it. First of all, I want to explain why I need this thing called index, because sorting will mess up the ordering, and the ordering matters, because this will become a radically different program if I just take this part and put it last. That means that all the off commands that are between here and there that trigger anything on that area will lose meaning. Yeah, so I will change the output depending on the order of the operation. So that's why I need an index, so to say, so that I can have an order of operations. Basically, at the end, when I get to the part when I'm applying the rules, I will just need to say, well, apply the rule with the largest index. But in order to apply the rule with the largest index, I kinda need the index. We can just add the index in the map here and say, well, return index is index plus 1. Let's have it run from 1. It doesn't matter, but this way we won't have a 0. It will look better if we are displaying it somewhere. So we are sorting this. So what do we do now after we have our commands? Well, I have another helper method here. And that is no, this is you, yeah. That says, well, take all the commands and separate them by x. Separate by x, and that takes all the commands, which is a command array and nothing else, and returns a what? A array of X interval segments. So what is an X interval segment? It's relatively simple. An X interval segment will have a from and a to, which are connected with the x-axis, and then they will have a list of segments which are y-interval segments. So now, instead of having all three coordinates basically having the same ordering and the same importance, no, I will say x contains y contains z. Y interval segment, and that is something that has a from and a to. Of course, I can write this with extends interval. Well, I don't actually need to do that when I look at it. I can just say extends segmented interval of y segmented interval. Yep. And y segmented interval extends segmented interval of z segmented interval. And of course, it will not be a surprise that z segmented interval, well, that will just extend interval. But we will need some other properties in order to have easier computation capabilities. So I will put in the y segmented interval, interval segment, interval segment. Yeah, this looks better. I will put here an xdiff value, which will be a number, which actually tells us, because we don't really care about where we are in the x area, we just care how much we are in the x area, and that's the width of the value according to x. And technically we could live with it without this, but it's nicer to have it. So the y interval will have an xdiff, and the z interval will have an xdiff and a ydiff. Oh, and the segments are actually something else. You know what? Let's go with the ones I already wrote. Yeah, this makes sense. Yeah, so this won't be an y integral segment, it will be an x segment. And what is an x segment? Those I will copy. Yeah, I know that we are leaving something. We need to have the coordinates, the froms and the tos. X segment, Z segment, no, Y segment, and this is actually yep, it makes sense. So these are actually the same numbers. Every z segment will have an x diff and a y diff, and those exact same x diff and y diff are here, but okay, we can live with it. So it is quite possible to have a better definition, especially as this is actually an interval. This is actually an interval. Yeah, so as you can see that x, y, and z, each of them has each x segment, so to say, each of them has the other two coordinates. Only the x has them as intervals, the y has x as just a number and z as an interval because it's not processed yet, and the z, which is actually the processed part, has both of them as just plain numbers. And if we have just plain numbers, we just multiply. We don't need to deduce anything. So how does separate by x works? We have all our x intervals, and this will be our bucket that we're using for each command. And actually I will call this command source, because I will right now, you know what the problem is? The problem is this part. The problem is this part because here we're gonna be changing the command. And if we are changing our input, and you might have noticed that the command is actually given as an input. Execute intersect is not a clean method. It doesn't return anything, for example. First of all the output it gives is actually contained within one of its parameters. So if we want to see the result, it's actually contained into all intervals. And it destroys the parameter we gave it, because after we're done, the command will be destroyed. So in order to preserve the original command, we might need it later, I will just go ahead and copy it. And this is the boring part, because hey, we can rewrite command. Yeah, command is containing of interval and interval and interval. Yeah, but the issue is that if I just do this will do a shallow copy only, so I need to specifically add x and y and z so they are copied as well. So not only command.action is copied over and it's not the same object, but I want to have command.x be copied over. So command.x.from is different from the other command source.x.from, because we could have a situation when command.x and command and command source are different objects, but command.x and command source.x are the exact same object. And you know what the simplest way to do that is? It's this. If you add the destructuring at the end, this will basically negate everything I've done before. So never do this. If you're doing destructuring with benefits, so to say, always destructure your source object first. So after that, for each command source, we get all the intersects. So these are the intersects. And I'm going about it the wrong way around, because that makes more sense to me. So if the other guy ends before we begin, we don't intersect. If the other guy begins after we end, we don't intersect. Everything else is an intersect. And this is relatively easy because, as I said, all the intervals are inclusive. So if it ends where we begin, we do intersect on one point only. Well, it is an intersection. So once we have that intersection, we can do a single check. Do we have any? Because if we don't intersect anything, we have a very clear situation. And note that the first command we process by definition won't have any intersects. It doesn't have anything to intersect with. So if we don't have any intersect, just add it. And this is our x segmented interval. So we have from and to, and we have exactly one segment that we're creating here, and that segment has those y's and z's, that index, that action. Okay, we're good to go. Yeah, and we're breaking out of the for loop, so we're taking the next command source. But if we don't have, if we do have an intersection, well, that means that we need to define our own segment. Actually, let's get back to this. And then we need to say, we need to execute the intersect. What was it called? Yep, it was called like this. And they takes some parameters. The first parameter is the actual intersects. The second parameter is the, I can definitely put all of this inside that. And I will try to do that later. It will delete some code. The second parameter is all the intervals, so we will have the x intervals, which is our result actually. The third one is the segment for our command. And that is why we need to define it here. That is the segment for our command, and we will give it as a parameter. Because each command actually defines a segment on x and y. Oh, and we cannot give our command because this thing requires an interval, but command.x is an interval. So this is, as I said, an unpure method. It will execute, it will do whatever it needs to get done, and after that we will have the results in x interval. After we're done, we just need to return the x intervals. So now, since we're here, I will just copy over and paste two more methods, which, if we really want to, we can roll them into one. It's separate by y when we're doing the exact same thing. Actually, we're sorting here to ensure that everything is okay. There is quite a few sorts that might not be needed, but it's better to sort when you don't need it, and not the other way around. We're defining a variable called y intervals, copying the command source, calculating the intersects in the exact same way. If we don't have anything to intersect with, add it to a push, otherwise execute the intersect. And one more small thing, because executing the intersect won't fill the xdiff, because it doesn't know about the xdiff, we will just fill it ourselves at the end. After we have all the y intervals, we just slap on the xdiff for each of them, and we just return them. Separate by z, same thing, only it has a y diff now. We have the z intervals. We are calling execute intersect with command.z, and we need to slap on two things, the xdiff and the ydiff, and we're returning the z intervals. So these are completely parallel methods, copy paste generated. If we try hard enough, I think that this could be replaced by a single method, but let it live. So, what does this thing miss? Oh, we missed the index. So now, the actual processing. And the actual processing is, well, it's gonna be somewhat underwhelming because it's essentially a triple for loop. We have a for loop for each segment where we are doing basically this code with a bit of fancy hand waving. Yeah, what did you try to suggest? Why do you do that? Yep. For that X segment, get the Y segments. For that Y segment, get the Z segments. For those Z segments, let's call it like this. For example, it's not gonna be this, but it's gonna be something else. And that's about it. A triple for loop. But we're gonna make it a bit more complicated than that because we're gonna add something like this. If we only have one segment, again, we don't need to do any separation if you only have one segment. If that segment is on, we need to multiply it, and the multiplication is the width of the X segment, which is this, the height of the Y direction, which is this, and the depth of the Z direction, which is this, and we need to multiply those together. Otherwise, get the Y segments, and if you have the Y segments, you just need to do the same thing again to speed it up a bit. If you only have one, multiply them, but now for X, we only use the XDiff that we already had. For Y, we use the width of our segment, the height, and for Z, we use the depth of the first segment. And now comes the different part, because for the Z segments, we're gonna calculate it anyway. Of course, we can have this thing once more. If there is just one segment and if it's on, then multiply xdiff times ydiff times the width of the segment itself. Depth, I guess. And otherwise, we're just getting a copy of the segments and sorting them. And note that we're sorting them by index inversely. So that means that we have the one that actually counts. Anything else we can just throw off. But the problem is that we don't know when to throw off until we need to throw off something. But this reminds me of an optimization. Basically, each time that we are doing a split, if we have segments, and these segments have the exact same everything. I'll need to think about it, but I think that if we have the exact same situation, no, that this is why we actually needed to separate them. Because we don't know which rules apply where. This is the first time when we have that only these rules apply here. Uh, the issue is that we have all those rules that all of them only apply here, and we can just take the last one, or the first one looking from the other end. And if it's on, I will even take the comment. If it's on, we add to our total count. If it's not on, no need to. That's all there is. We actually don't need this part because this will be taking care of it either way. Yeah, if we only have one rule, this will be the last one by definition. Yeah, sorting of one item of a one item thing, it's not really that much. But these ones, the other ones are important because we don't want to do any separation. But on the other hand, the separation will only have one segment. You know what? Let's run it as this. So with this input. And I'm gonna need to do a small change in run task so that it actually runs the good one. We'll see if it's the good one. And the input is the smallest possible. And it says it's 0. And it's not 0. It's definitely total lit. That's the total number of lit cubes. And that's better. We got 39 in 4 milliseconds instead of 57. Let's look at the bigger example. This one, which was actually part 1. Looks okay. Brute force and the thing. The second thing runs actually twice as fast. It's not that it's slower, it's faster. Well, it is faster than brute force. Let's try another example. Let's try our actual input, but only for the first task. So this will actually be the correct code for the first task. And the solution that we gave was this 533,863. Let's see if both parts give us the same solution. Yeah, 533,863. That's great. So let's try it on the example for the second part. This might take a while. Actually, it didn't take a while. It only took 200 milliseconds, which means that our algorithm is not only correct, it's fast as well. Okay, that was a bit unexpected, but I'll take it. And now, the moment of truth. Our actual input. And hopefully now this won't just block and stay there, otherwise I might need to eat my hat. And since it's winter around here, it's a big woolly hat. No, it just took a second and a half to spit up this huge, ridiculously huge number. Just let me check the number of digits of this. Yeah, we're okay. Because the max safe integer has 16 digits but starts with a 9. But we're getting dangerously close. That was another thing that I was afraid of. That if we needed to subtract somehow, Note that we are constantly adding to this part, but if we needed to subtract somewhere, we might have gone into unsafe territory. No, I need this tab. And let's check right now. That's the right answer. What is the probability to get a 16-digit number right on the first? That's the right answer, and we are just one gold star off from the end, because we are getting one extra. 49 to go. You don't have enough strength to boost the signal. We just need one more, and that one more is the 23rd task, which we'll be getting on soon. So one more, and then we have the big finale. Anyway, you can see that I did manage to make a quite fast solution, and let's try that. Do we have run all? Yep, 22 is there, 19 isn't, because it takes 20 minutes. Let's take everything except 19 in place. And we have our obvious candidates for optimization. Fortunately, 22 is not one of them, but 25 definitely is. And we get this nice large number. We have task 12, which takes 7% of the execution time, 18 takes 6%, 22 takes 6%. Okay, we can live with those. 23 takes 13%, and then we have 25 with 57%, and no idea how to optimize it, as it's straight up simulation. We will need to do some maybe micro optimizations, because in those kind of cases even a minimal optimization that we're doing 2 million times will help with the runtime, which is at current at 27 seconds for 24 tasks. And yeah, this one is not implemented, and you can see that we're skipping from 18 goes to 20. We're ignoring task 19. So that is about everything that I wanted to show you. We managed to get one more star, and we're one star away from the grand finale. Bye for now, and keep developing.